that chemical equation, we're going to have to figure out a way to convert the amount that we use in the lab, which is grams, to the amount we see in the equation, which is moles. Can you convert grams of something to moles of something? I'm sorry, let me rephrase that. Should you be able to convert grams to moles? Yes. Yes, you should be able to, right? Did that all last week. That's your molar mass calculations. So once we get to moles, then the whole equation opens up for us. All right, so in lab, we use grams, right, or even milligrams, for instance, or kilograms, for etc. So we need to convert this to moles before using the balanced equation. Right, the equation gives you a mole-to-mole ratio. It doesn't give you a mass-to-mass ratio. So it's only helpful to us once we get to moles. Okay, and I'm going to put this here in thing, or starred. I'm going to say get to moles. Okay, that's a theme, or that's a something you should always keep in mind, not just when it comes to stoichiometry, but as we'll see when we start talking about gases in chapter 8. All right, your book has a really good sort of pathway to follow. Once we start going through now, getting from grams of something to moles of something, and then using our balanced equation to help us figure out how much of a product or something else we can make in our balanced equation. So that may look a little confusing right now, so let's walk through an example of how we actually use that in a calculation. All right, so we've seen this equation 8 minutes ago, and it's the equation, a combination reaction where nitrogen reacts with hydrogen to make NH3, which is ammonia. Now we're told that we want to determine the mass of NH3 that we can make if we start with 32 grams of N2, nitrogen, in that equation. And we've already confirmed the equation is balanced, yes? Okay, so we don't need to mess with that. So we're going to use the same strategy we've used in the previous questions. What are we given? What do we need to get to? So we're given here what?
32 grams of energy.
We are told that we are starting with 32 grams of N2. And we need to figure out how many grams of NH3 we can make. Right? So we're trying to relate the N2 to the NH3. Do you think we can go from grams of one thing to grams of the other in one step? If the answer to that is yes, what can we use to do that in one step? So if you said yes, you have to tell me what you're going to use. Somebody said yes. A couple of people said yes. I heard yes. What equation, I'm sorry, what relationship does the balanced equation give us? Right, we're relating the nitrogen to the ammonia. Does this tell me, or does this give me a gram to gram relation, or does it give me a mole to mole relation? It's a mole to mole relationship, right? It's not a mass to mass relationship. So if I'm going to use my equation, which gives me a mole to mole relationship, I'm going to have to convert my grams to moles first, before I can use that balanced equation. Right? So if I'm starting with my grams of nitrogen, I would have to first of all convert this to moles of nitrogen. grams of N2 to moles of N2. How can I get there? What am I going to use?
For every one into.
We use the molar mass of a substance to convert from grams to moles. Right, so 1 mole of N2 is, if you have a periodic table, one nitrogen, I think it's about 14. 14, so we have 2 of them, so that'll be 28.02 grams of N2. Right, the molar mass is the mass of 1 mole. That's what it means by definition. It relates the moles to grams, so we can use it to convert between the grams and the moles of N2. We need to get to moles of nitrogen, right, for a couple reasons, but the most important reason is we set it up here, right? It's in red and it's highlighted and it's starred, which means we have to do it. Get to moles first. So we're going to convert our grams of N2 to moles of nitrogen. Once we get to moles of nitrogen, right, then the whole equation is going to open up, because now I can use the moles of nitrogen that I have along with my mole-to-mole ratio to figure out how many moles of ammonia I can make, the NH3. So I can now get to moles of NH3, and what am I going to use to get from moles of one thing to moles of the other? Moles of one to moles of the other, from the balanced equation. The molar ratio, which is just the coefficient, right, the small whole number. So this tells us that we have 1 mole of nitrogen for every 2 moles of NH3. So we're going to use the mole-to-mole ratio. Right, so 1 mole of N2 for every 2 moles of NH3, or we just flip it, depending on the units that we want. Once we get to our moles of ammonia, then we can convert that back into grams of ammonia. Moles to grams, what do we use? Molar mass, right? The molar mass allows us to go back and forth between those. We're going to use the molar mass of NH3. Okay, we'll do a quick calculation. So 1 mole of NH3 is 17.02 grams. So you cannot get from grams of one thing in an equation to grams of another thing in one step. Right? You can get there, but you can't get there in one step. You have to go through moles. You must. Right? So convert grams to moles first. We use the molar mass. Then we use the mole-to-mole ratio from the balanced equation to get to moles of the other thing. And then we can convert that thing back to grams using the molar mass of the thing at the end. All right, so let's set it up and see how it makes sense, both in terms of the units, but also in terms of the relationships that we're using. So we start with what's given. We have 32 grams of nitrogen. And our first conversion factor here comes from our molar mass. We're going to take this and stick it in. So in my first step, I want to end up with moles of N2 as my unit. Right? So I'm going to put the moles of N2 on top and the grams of N2 on the bottom. So it cancels out with the grams at the beginning. 1 mole of nitrogen for every 28.02 grams of N2. Grams of N2 go away. That should not look foreign to you. Okay, that should look familiar. You did that we did that last week. Did a lot of them last week. grams to moles, moles to grams. Use the molar mass. The only new thing that we just introduced today is the next step, right? Which is that mole to mole ratio that comes from our balanced equation. We just look at the coefficients, express them as a mole to mole ratio. So this next step here is to use that ratio, so we end up with moles of ammonia as our unit, which means we're going to choose this one, right? That has the moles of ammonia on top. So 2 moles of NH3 for every 1 mole of N2. Moles of N2 go away. Right? Your units are telling you where to put them. So don't just put numbers in, put the entire unit. Our last step would be to go from the moles of ammonia, NH3, to grams of ammonia using the molar mass of ammonia, right? That again is something that we've seen already. We're going to take that now and stick it in here, right? And if you want to end up with grams, the grams are going to go on top, 17.02 grams of NH3 for every 1 mole of NH3. Moles go away. And we end up with grams of ammonia, which is what we needed. So my units make sense. Right, I only have 1 unit left, which is the unit that I wanted to be left with from the very beginning. All I have to do is now to use my calculator, right? So what do we get? I forgot my calculator. Three? 38? 38? 38? This side of the room? 39? Okay, I should have 2 sig figs, right? Because my original number here has 2. Right, that has 4. This is unlimited. That has 4. 39?
Yeah.
39 what? Apples? 39 grams of NH3.
I have a question.
Yeah.
So to find the, to go from grams to moles, do
Yes.
we have to do it like the way that you did it, or are we able to get the grams to moles before we do everything else? If that makes any sense. Like figuring out the math of how a mole of N2 equals 28 grams of N2.
Right.
We went from 32 grams of N2. So to figure that, can we figure out that math before we do everything else?
Yeah,
Or do
you
we
can.
have to go by the way that you did it?
So this is the way that makes sense in terms of how you would, where you would start and where you need to get to. So I guess I'm not quite understanding. So you're saying, can you put this first?
No, I'm not talking about that part. I'm talking about the top part. So you know how you went from 32 grams of N2
Yeah.
and then you found the moles of N2,
Right.
and you did the same thing for the NH3.
Yes.
Can we figure that out before we continue with everything else?
Yeah. You can,
Okay.
It doesn't matter when you figure the things
Okay.
out, right? But how you put them in here, though,
So,
should
yeah.
make sense, right? So, we just did it that way because that's the order that we took. But you can figure those out afterwards. So, in this particular problem, right, we were given grams of a reactant N2, and based on our stoichiometry, or just based on the balanced equation, we were able to figure out how many grams of the product, the ammonia, that we could actually make. So if everything worked out perfectly and we started with 32 grams of N2, we should be able to make 39 grams of ammonia. This is extremely important when it comes to, maybe not minor reactions like this, but when this is done on a huge scale, like on a commercial scale. Right? Ammonia is a very, very important starting material for making other important things like fertilizers and explosives. So people run this reaction on a huge scale. So if they know, for instance, how much ammonia they want to produce, they can work backwards and figure out how much nitrogen they need and how much hydrogen they need. So they don't have to waste their money buying too much or run into a situation where they don't have enough of a particular reactant. So, we're doing a simple example here in class, but this is actually done on a much larger scale in any chemical industry that you can think of. Right? Stoichiometry is at the heart of pretty much all chemical reactions. The other thing I want you to notice here is all we're doing, right, as we go from one step to the next, is we are changing the unit. We go from grams to moles to moles, then moles to grams. That's the same thing we did when we looked at our metric conversions at the very beginning. We went from centimeters to meters to kilometers. It's unit conversions that you're doing, except now in a chemical equation or chemical reaction. And we're using the same tools, right? Equalities that we can make into conversion factors. Flip them depending on what units we want to cancel out and what we want to end up with. So it may not seem, when we first introduced the dimensional analysis technique way back when, right, it seemed like I was trying to torture you. Okay, it's not, it's useful. It's very, very useful because you can use it in lots of applications.
How you did the 17 point, how you got the molar mass of grams of NH3 and you did it over 1 mole? Will it always be 1 mole?
The molar mass is always per mole.
Okay.
Always. Yeah, so 1 mole of that thing. Right, so even the nitrogen here, right, is for every 1 N2. So
there's never a time where it'd be like, it's something other than 1.
It shouldn't be, no. If you're talking about molar mass, it has to be for 1 mole. Now, when you get comfortable with these types of calculations and you start combining steps, okay, then you may see different things pop up. But as you're starting off and you calculate the molar mass, it's always for 1 of something. Always. Okay, let's take a look at one more. Where did it go? I thought we had another one down here. Oh, there it is. Okay, so here we have the reaction between hydrogen and oxygen, and we're told that it produces 13 grams of water, H2O. We need to figure out how many grams of the oxygen O2 reacted. So what are we given? Right, just getting organized is oftentimes the rate limiting step in these types of calculations. So just getting organized here, we want to make sure that we have everything sort of laid out for us. So what are we given? We're given 13.1 grams of H2O. And what do we need to find? The grams of O2. So grams of O2. Can we do that in one step? No. All right, so we want to first of all convert the grams of water into moles of water. What am I going to use to do that? We use the molar mass of H2O. Okay, and if you check your notes, you calculated this last week. So every 1 mole of H2O is 18.02 grams of H2O. Okay, remember, to get the molar mass, you simply add together the individual molar masses. And where can you find the individual molar masses? Periodic table, which you will always be given. Do not memorize molar masses.
It's hard not, well,
If it happens to stick in your brain, that's great, but don't spend the extra mental ATP or energy trying to stick it in there, okay? That's a waste of your time and energy. Okay, once we get to moles of water, then we can convert that to moles of O2. So moles of one thing to moles of the other, what are we going to use?
the coefficient.
The coefficients or the mole to mole ratio? Right, so from the equation we are relating the oxygen to the water, right? So for every 1 mole of O2, we have 2 moles of H2O. I just put the coefficients over each other. Once we get to moles of oxygen, we can convert it to grams, and we're going to use the molar mass of O2. Right, so 2 oxygens, 1 mole of oxygen is 32.00 grams. Do the steps make sense?
Yeah.
Right, we're breaking it down from one big huge jump into a couple chunks or a couple bite-sized pieces that has to go through moles, right? Because the mole ratio is the only thing that we get from the equation, right? And the equation is a thing that relates one thing to the other thing. All right, so when we set this up, we're going to start with what's given. So we have our 13.1 grams of water. All right, we're going to take our molar mass, we're going to insert it in here. We want to end up with moles, so moles has to go on top. 1 mole of H2O is 18.02 grams of H2O. The grams cancel. All right, then we take our mole to mole ratio from the balanced equation to convert the moles of water to the moles of oxygen. So in this case, I only wrote one of the conversion factors, but it's the right one. So 2 moles of H2O for every 1 mole of O2. Moles of H2O go away. And then our last step, right, we want to convert the moles of oxygen to grams of oxygen. So we use our molar mass. And again, the units are going to guide us. The moles has to go on the bottom because we want to end up with grams of O2. So 32.00 grams of O2 on top. Moles go away. So our units make sense, right? Because that's what we wanted. That's the only unit left. Right? We have no stray units left over. And our molar masses make sense as well, right? Because we did that one last week, and then oxygen 16 times 2. Okay, and then what do we get for an answer on this one? 11.6. Confirmation, 11.6, somewhere. 11.6 grams of oxygen. That's stoichiometry in a nutshell. It's a pretty big nut. It has a shell just as big. So, you know, when you first do a couple of these things, right, it may seem a little daunting and a little challenging, but you want to slow down a little bit, right? Think about what it is that you're doing. And the units here are going to guide you, right, just like they've always done. but you also want to make sure that you set up your equations, not your equalities and your conversion factors properly, right? This stoichiometry does not work unless you have your balanced equation, right? That's at the center of every single stoichiometry calculation that you will ever do.